while we're talking about other reducing agents that can affect transformations that lithium aluminum hydride cannot, I want to jump ahead to chapter 21. Which is amines, and talk about another special reducing agent. And that's sodium cyanoborohydride. So it's sodium borohydride that has a CN group in place of one of the hydrides. Though it's not possible to write a resonance structure because there's no lone pair on boron. Negative charge is not there because there's a lone pair, it's there because it has an excess electron in its Lewis structure. It is a lower reactivity borohydride because of the electron withdrawing nature of the cyanide through an inductive effect. And thus, sodium cyanoborohydride is less reactive than sodium borohydride itself. So we've pulled a similar trick that we pulled when we made the lithium triterbutoxy aluminum hydride. Where we reduce the activity of the hydride by putting these electron withdrawing inductive groups. By putting a cyanide group on there. Sodium borohydride is already not reactive enough to reduce esters or amines. And sodium cyanoborohydride is even less reactive. So you can reduce nitriles to amines which are limited to primary amines. And as it turns out, you can also reduce azides to amines. Using lithium aluminum hydride. Both azides and nitriles, however, are limited to production of primary amines. Because in both cases, you have a nitrogen that has no R groups except for the one carbon that it's attached to. Both of these methods actually allow us to start an alkyl halide and generate from it an amine, because we know that we can react the alkyl halide with either sodium azide in the MSO to generate the azide through an SO2 reaction, or with sodium cyanide in another polarity coating solvent. The DMF and the DMSO are interchangeable here. So we can generate an amine that either has the same number of carbons through the azide or one additional carbon through the nitrile by first doing an SM2 displacement with cyanide or azide and then reducing with lithium hydride. But it's limited to primary amines. Sodium cyanoborohydride, on the other hand, is a reagent that will allow us to convert carbonyl compounds into amines in a single step for a process referred to as reductive amination. And we'll see that it involves a similar mechanistic trick to the lithium triterpenoxy aluminum hydride reduction of acid chlorides. And it allows us to make primary, secondary, or tertiary amines. Directly from carbonyl compounds. So, for example, if I started with benzaldehyde and I treated benzaldehyde with aminoethane in the presence of sodium cyanoborohydride, and a little bit of acid catalyst, I can generate the corresponding secondary amine. In a single step. The key is that this is reactive enough to reduce intermediate salt. But not an aldehyde. The medium salt is positively charged and is therefore significantly more reactive towards reduction than the neutral aldehyde. So what's happening is the primary amine in the presence of the catalyst is reacting to generate the aminium salt, and then the aminium salt is being intercepted by the reducing agent. So really, it's not a new mechanism. It's a mechanism that you're already familiar with, whereby your catalytic acid and your nucleophilic amine are going to add the amine across the carbonoxygen pi bond. In the mechanism that you are familiar with. Rather than writing out CH2, CH3 every time. And then we do 2 proton transfers to generate water as a leader. Proton transfers, right? First, we take the proton, or put a proton on the oxygen, then remove it from nitrogen to generate the anion now. 5 of the 6 steps of imine formation. In the absence of sodium cyanoborohydride, the next step would be to deprotonate that positively charged nitrogen to generate the imine. But in the presence of sodium cyanoborohydride, that iminium salt is intercepted by a hydride hydride addition produces the amine if it were ammonia instead of ethylamine, we would have NH2 here, and we would have generated a primary amine. If we used diethylamine, then there would be another ethyl group there, and the aminium salt, rather than forming an enamine, would have been intercepted. In this case, no enamine would have been possible anyway because the phenyl group has no alpha hydrogen. So the mechanism of the reductive amination is the first 5 steps of imine formation, which you're already intimately familiar with, followed by intercepting the reactive positively charged vanadium ion with the reduced reactivity borohydride reagent, sodium cyanoborohydride. And it's a good way of making a variety of amines. It doesn't involve strongly basic reagents like lithium aluminum hydride, and it's amenable to the production of primary, secondary, and tertiary amines rather than being limited to primary amines. We'll see other examples of amine synthesis toward the end after the second exam, where we take up the rest of the amine forming reactions and reactions of amines. And you will see another example of intercepting the aminium ion with a reagent that's reactive enough to react with the aminium ion, but not reactive enough to react with the parent carbonyl compound in a reaction called the